Good afternoon, everyone. Uh, my session is on application of MATLAB in design of machine elements, but I'm going to stick to one particular concept that is theories of failure under static loading, and I've developed some codes in this particular section. Uh, Before we go to the MATLAB code, first of all, let me introduce you to what are these theories of failure. Let me start up. As we said, for static loading, any external force acting on a machine component, it is called as a load. And these loads, they fall under two categories: static load and dynamic load. Static load is a load which is dead or steady. That means there is no change in magnitude or direction. Whereas dynamic loads, the magnitude or direction will change. It can be a live load where the magnitude continuously increases or decreases, or it can be a shock load or a suddenly applied load, or suddenly from zero you may apply directly a 100 Newton load, or it can be an impact load. The difference between a shock load and impact load is shock load is applied without any height of fall or initial velocity, whereas impact loads we apply with some initial velocity or height of fall. If you observe, dynamic loads are changing continuously, whereas a static load, there is no change in magnitude or direction. And this particular section, we are talking about design for static loading. Now, whenever there is a load applied on a component, there is a resisting force developed inside the member. Whenever there is an external force acting on a machine component, there will be internal forces set up. These internal forces, you can see here, when I apply a force F here, there is an internal force which opposes that applied load. But this internal force, we call it as a resistance. The internal force set up inside the member is called as a resistance. This resistance per unit area of the material is called as stress. Now, under limiting conditions, we say for the material to be safe, this resistance should be at least equal to force applied. That's how stress is force per unit area. Now, these stresses, it can be simple stresses or it can be compound stresses. Generally, in simple stresses, we have two types of stresses: normal stress and shear stress. If a force is acting perpendicular to the plane, then it is called as normal stress. If the stress is acting along the plane, it is called as a shear stress. And under a normal stress, we have tensile stress, compressive stress, bending stress, bearing stress. Under shear stress, we have transverse shear and torsional shear. Now, if we look at this simple stresses, you see that the stress induced because of equal and opposite pulls is called as tensile stress, and the computation of this stress is load by area. Compressive stress is a stress induced due to two equal and opposite pushes, and how to compute this? Again, it is load per unit area. Then, when a member is subjected to bending, then the stress induced is called as bending stress, and this bending stress is obtained by applying the bending equation: M by I is equal to sigma by Y is equal to E by R. We all know that sigma is equal to M by Z. Then bearing stress, when you can see here, the journal is bearing with the bearing surface. Even in riveted joints also, the circular face bears with the plates. So bearing is always a projected area. Bearing area is always a projected area, and hence the bearing stress is P by D into T into M. These are all normal stresses. You can see the notation also. Sigma is the symbol that is being used for normal stresses. The second set of stress, we call them as shear stresses, which are parallel to the surface. If two equal and opposite tangential forces are applied, then we call it as transverse shear. If you observe, there is a rivet here. If there is a pull applied, then two equal and opposite tangential forces are set up, causing shearing off at one place, and this we call it as single shear. If it breaks into two parts by shearing off at one particular section, then it is called as single shear, and the resisting area available to resist this shear is pi by 4 d square. Now, same thing, if you observe the butt joint here, double cover butt joint, the rivet will break into three pieces. That means it is undergoing shearing at two sections. So we call this as double shear, and the area that is available for resistance is 2 into pi by 4 d square. Then we have another called as torsional shear. An example I can give is opening and closing of the cap of a bottle, right? So we are applying two equal and opposite couples. If we apply two equal and opposite tangential forces, it is called transverse shear. If we apply two equal and opposite couples, you can see here, one couple I am applying in counterclockwise direction here. On the other side, I am applying clockwise couple. And together, it will form what is called as torsion, right? And we are applying what is called as torque, and the stress induced is called as torsional shear stress. And the computation is done by using the torsion equation. T by J is equal to tau by R is equal to C theta by L. The values for J and Z are available from the data handbook for different sections. Now, let us look at what is the difference between normal and shear stress. Let us say there are a number of forces acting on a body producing a resultant stress inside, and let that total resultant stress be T, acting here at an angle alpha with the vertical. If I resolve this into along a direction perpendicular to this plane, right, we call it as sigma z. Sigma z is equal to T cos alpha. That is the normal stress component. Then same thing, if I resolve it along the plane, it is called as the shear stress component. Tau z is equal to T sin alpha. This component in turn can be resolved into two rectangular components, one along x direction, another along y direction. Now tau z resolving along x-axis, then it is tau zx is T sin alpha cos beta, and if I resolve it along tau zy is equal to T sin alpha sin beta. That means there are totally three stress components on one plane here, one normal stress and two shear stress components. And the notation of the symbols that are being used, we observe Z. When I put Z here, that indicates the plane. This is the Z plane. So sigma ZZ it should have been. ZZ now is equivalent to sigma Z. And the other one, X, is the direction in which the force is acting. Right? One is the first one is the phase or the plane. Second one is the direction. Now, if you take a 3D setup, this is on one plane. For a 3D, there will be three different planes. So that means there will be three normal stresses and 6 shear stress components. We call this as 3D state of stress. Of course, tau xy, tau yx, tau zx, tau zx, tau yz, tau zy, they are complementary to each other. In that way, we have 3 normal stress and 3 shear stress components. Now, if you observe, all these 9 components, they are functions of these inclinations. If I change the orientation of the element, stress element, then the values of alpha and beta will change. That means all these 9 stress components will undergo variation. Now, when I go on varying the position, that means orientation, at some particular orientation, all the shear stress components will become 0 and will be left with only 3 normal stresses. You can see here 3 normal stresses, sigma 1, sigma 2 and sigma 3 is what we call them. Then these 3 stresses we call them as principal stresses, and the planes on which they act, they are called as principal planes. The principal stresses are the normal stresses acting on the planes on which there are no shear stress components. So principal planes are the planes on which there are no shear stresses or shear stress components, and principal stresses are those normal stresses which are acting perpendicular to the planes on which there are no shear stress components. Right? So this is about principal stress. Now, in 3D, we have 3 principal stresses, sigma 1, sigma 2, sigma 3. If I am given a 3D state of stress, then I can get the principal stresses by transformation called as eigenvalues. Right? We have one command called eigenvalues, then we get all the 3 principal stress components. Now, as I said, principal planes are the planes on which there are no shear stress components, and the principal stresses are the normal stresses acting on these principal planes. At this point, I will introduce you to theories of failure. With this background, I will introduce you to the theories of failure. Now, generally, failure is of 2 types: failure by yielding and failure by fracture. If a component breaks up into pieces, it will undergo fracture. That is without yielding. We call it as failure by fracture. But there are components which undergo yielding. They extend before the failure. So, but many a times, the moment the permanent deformation sets in, they no longer are useful. We can say failure has occurred even though they have not broken into 2 pieces. The moment the permanent deformation sets in, it loses its functionality. So generally, failure by yielding, the material may have to be replaced just because it has lost its functionality, not that it has broken into pieces. Whereas brittle materials, they don't yield, but they undergo fracture failure, and they break into pieces which we need to replace. Some of the examples where we see why exactly these theories of failure. Now we have seen here, we have 9 stress components, 3 normal and 3 shear stress. Here also we have shown this, right? Simple stresses, normal stress and shear stress. As long as only one type of stress is induced in a material, we call them as simple stresses. Suppose if there is a combination of normal and shear, then we call them as compound stresses. Compound stresses are a combination of normal and shear stress. Now, in that sense, let me take one example here. Find the diameter of a link stock. If the tensile stress in the link material is not to exceed 75 MPa, then determine the size. Okay, fine. Now, the type of stress that is induced here is tensile stress. So if I have to find out the diameter, A is equal to pi by 4 d square. Now it is easy for me to find out the diameter easily because I know what type of stress is induced. It is a tensile stress. I take one more example. A pull of 80 kilonewton is transmitted from a bar. of X to bar Y through a pin, if maximum permissible shear stress in the pin is 80 Newton per mm square, find the diameter of the pin. Now, if you observe again, there is a double shear happening here because X is pulling in one direction, Y is pulling in between, and we have the pin. The pin will shear at two places and there is a double shear. So the stress that is induced inside the pin is a shear stress. And I am very clear about it. So in both these cases, because I know the material property, one is tensile, the other one is shear. But when there is tensile stress, there is only tensile stress, there is no shear there. Where there is shear, there is only shear, there is no tensile. So the failure criteria is clearly known. This fails by tension, this fails by shearing. So I have to, in this case, I have to keep the material safe under tension. Here I have to keep the material safe under shear. And this is very clear because only one type of stress is acting there. But if we take an example where I have both normal as well as shear. Here you can see here. There is a twisting moment of 120 Newton meter. That means torque is there. So torsional shear stress is induced. An axial thrust and bending moment. Again, there is a combination of axial and as also a normal. Bending moment also produces normal stress. So there is a combination of normal stress as well as shear stress. In such case, what is the failure criteria and where it is critical? Is it critical under normal stress or is it critical under shear stress? Where I should keep the material safe, under shear or under normal stress. So what is happening? Many studies have been undertaken on such components which are subjected to, you can see there are many such examples: IC engine crankshaft, power transmission shafts, spindle of a screw jack and bolted welded joints, eccentric loading, ceiling fan. So many places we have a combination of sigma and tau. Now what exactly is happening? When materials are subjected to these combinational loads, the type of stresses that are induced can be normal stress. Simultaneously there will be shear stress. Now whenever there is a load, there is a stress, and according to Hooke's law, whenever there is a stress, there is an accompanied strain. So I have a normal stress, I have a shear stress, I have a strain, and whenever we are subjecting a material to some applied force, whatever energy is input, it is absorbed by the material in the form of strain energy. And this strain energy, it can be total strain energy. Total strain energy is volume strain energy without distortion plus distortion strain energy. That is called as the total strain energy. Or simply without considering volumetric strain, as distortion is too high, in that case volumetric strain can be neglected. Then it will be distortion energy, strain energy. So all these phenomena are happening inside the material simultaneously. Now, how do we know under what conditions the material is undergoing to fail? For that, many scientists, they have proposed their own theories. That again depends on what type of material they have used. Each person has used a different material and hence arrived at a different result. And these results is called as theory of failure. One result is one theory of failure. Maximum principal stress theory or Rankine's theory, maximum shear stress theory or Guest's theory or Tresca's theory, maximum strain theory, principal strain theory or Saint Venant's theory, total strain energy theory or Hicks theory, or maximum distortion energy theory or von Mises and Hincke's theory. Now, let me take through each one of them. Maximum principal stress theory, according to this theory, says failure occurs when the maximum normal stress, which is nothing but the principal stress sigma 1, becomes equal to yield point stress or elastic limit stress under simple tension test. All these 5 theories, only one type of testing is used, that is a simple tension test under UTM. Now, the first theory says when the principal stress sigma 1 becomes equal to sigma E, then the material will undergo failure. And this particular theory is especially useful for brittle materials and not suitable for ductile materials. And if the material is failing because of sigma 1, then I should keep it safe there. So for safety, I will divide the yield point stress with a factor of safety. Then when sigma 1 is restricted to sigma E by n, then the material will remain safe. If sigma 1 is allowed to reach sigma E, the material will undergo failure. If sigma 1 is restricted to sigma E by n, then the material will remain safe. This theory is called as principal stress theory. Second one is maximum shear stress theory. Here it says failure occurs when the maximum shear stress induced inside the material during simple tension test, when it becomes equal to shear stress at elastic limit, then the material will undergo failure. So the condition here will be sigma 1 minus sigma 2 divided by 2 is equal to sigma E by 2. The 2 cancels there. So sigma 1 minus sigma 2, if it is allowed to reach sigma E, then the material fails. Now, how to keep it safe? Restrict the value of sigma 1 minus sigma 2 to a value sigma E by n. That means dividing the yield point stress with the factor of safety, I get the allowable stress or safe stress. So if the stress is sigma 1 minus sigma 2 is restricted to sigma E by n, then the material remains safe. Now, for a triaxial state of stress, which is we have sigma 1, sigma 2 as well as sigma 3, then whichever is larger between sigma 1 minus sigma 2, sigma 2 minus sigma 3, sigma 1 minus sigma 3. So that should be kept within sigma E by n. The third theory is maximum strain theory. According to this theory, during the simple tension test, when the maximum strain induced in the material becomes equal to the strain at elastic limit, then the material undergoes failure. That means maximum principal strain is epsilon 1. If epsilon 1 becomes equal to epsilon E, then the material will undergo failure. To keep it safe, we have to divide with the factor of safety n. So if same thing is expressed in terms of principal stresses, then it is sigma 1 minus mu sigma 2 should be restricted to sigma E by n. For biaxial, if it is a triaxial, even sigma 3 is involved, then sigma 2 and sigma 3 are lateral strains. So sigma 1 minus mu into sigma 2 plus sigma 3 should be restricted to sigma E by n. The fourth one is strain energy theory or H theory. Now it says the failure occurs when the total strain energy per unit volume becomes equal to the total strain energy per unit volume at elastic limit during the simple tension test. Now, the condition is like this: root of sigma 1 square plus sigma 2 square minus 2 mu sigma 1 sigma 2 it is allowed to become equal to sigma E. That is the total strain energy. We are talking about the total strain energy. When it becomes equal to strain energy at elastic limit, then the material undergoes failure. This is for biaxial. Triaxial, in sigma 3 is present. Sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 mu sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1 whole power half. That means under root. If it is restricted to sigma E by n, then the material remains safe. This is for total strain energy. This particular theory is especially applicable if the hydrostatic stress conditions exist. That means all the three principal stresses are equal. Then distortion energy If they are not equal, then we have to go for distortion energy theory or von Mises theory. Here it says the material undergoes failure when the distortion energy during the simple tension test becomes equal to distortion energy per unit volume at elastic limit. Then the material undergoes failure. So that is root of sigma 1 square plus sigma 2 square minus sigma 1 sigma 2 is equal to sigma A. If this condition prevails, then the material undergoes failure. This is for the biaxial state. Triaxial state is there. Sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1 under root. If it is restricted to sigma E by n, then the material remains safe under distortion energy theory, and this is especially useful for ductile materials where we don't have a hydrostatic stress condition. Now, there are 5 different theories we have observed, and which theory has to be applied to which type of material, where we have to apply all this is what is a lot of confusion and dilemma. So one simple understanding analogy I can give is say there is a running race. A simple analogy to make it more simple to understand. Let us say there is a running race. Now what is happening? There is a sigma 1. There is a sigma 1 minus, that is maximum normal stress sigma 1, then maximum shear stress tau maximum, then maximum strain epsilon 1, and there is total strain energy, and there is a distortion energy. 5 different phenomena are there. Now all these 5 are happening inside the material simultaneously. There is one type of load that is acting, but 5 different parameters are changing simultaneously. Now let us say this as an analogy to a running race. In the case of a running race, the target line is same for all, whereas here target line is different. That's the difference between that running race and this race. Now each parameter has its own threshold. Each parameter has its own threshold. If I say sigma 1, let us say that its threshold is 100. Once it crosses 100, the material undergoes failure because of first theory, maximum principal stress theory. Then if suppose maximum shear tau max, let us say its target is 50. Suppose if tau max crosses 50, then the material will undergo failure because of maximum shear stress theory. Then third is maximum strain. Let us say 2 is the maximum strain, that is the threshold value for strain. If maximum strain reaches the value of 2, then the material undergoes, let us say, that is the threshold. Once it crosses 2, then the material undergoes failure. Now, the total strain energy, let us say it is, let us say 500. Now, that is one number I am giving just for illustration. If it crosses 500, then the material undergoes failure because of total strain energy. And distortion energy, let us say 400. If distortion energy crosses 400, that is a threshold, then the material undergoes failure. Now each one, sigma 1, tau maximum, epsilon 1, then total strain energy and distortion, each one has its own target now. If whichever crosses this target first, then the material undergoes failure according to that. Now, once we start increasing the load, automatically sigma 1, tau maximum, epsilon 1, distortion energy and total strain energy all are increasing, and whichever reaches its threshold first, the material undergoes failure because of that particular reason. So let us say if epsilon 1 reaches 2 first, before sigma 1 reaches 100, before tau maximum reaches 50, before total strain energy reaches 500, before distortion energy reaches 400, if epsilon 1 crosses 2, then the material undergoes failure because of maximum strain theory. Now this is about the different types of theories. Now how do we apply that? Let me take 1 or 2 numericals and apply it and see how MATLAB is of use with here. Now let us consider one example here. A material has a maximum yield strength in tension compression. Sigma y is equal to 100. That is the yield point stress. Then compute the factor of safety using various theories of failure. The principal stresses are given as sigma 1 is 70, sigma 2 is 70 MPa, sigma 3 is 0. Poisson's ratio is 0.3. First, let me solve it by conventional method. Now I will apply all the 5 theories of failure and find out the values for the factor of safety. Let me apply the first theory. There is a maximum normal stress theory, right? It says sigma 1 is equal to sigma E by n. Therefore, n is equal to sigma E by sigma n. Sigma E is the yield point stress, that is 100. Sigma 1 is 70. So this is 1.43. Then according to maximum shear stress theory, I have to, if sigma 1, sigma 2, sigma 3 are there, then I have to find out which is maximum. Sigma 1 minus sigma 2, sigma 2 minus sigma 3 minus sigma 1, whichever is maximum. Here sigma 3 being 0. So maximum of sigma 1 minus sigma 2, comma sigma 1, comma sigma 2, that will be 70. So factor of safety will be 100, that is yield point stress, divided by maximum of these 3 will be 70. So n is 1.43. Third one is the maximum strain theory. According to this theory, the sigma 1 minus mu into sigma 2 plus sigma 3, if it is restricted to sigma E by n, then the material remains safe. So n is equal to sigma E by sigma 1 minus mu into sigma 2 plus sigma 3, but anyhow sigma 3 is 0 here in this case. So the value of n will be 2.04. Then I'll apply total strain energy theory. That will be sigma 1 square plus sigma 2 square minus 2 mu sigma 1 sigma 2 is restricted to sigma E by n whole square. Then the material remains safe under total strain energy theory here. So the value of n will be sigma E divided by root of sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 mu, all this, but sigma 3 is being 0. So I get n is equal to 1.207. That is based on total strain energy theory. Then last one, distortion strain energy. Here it is n is equal to sigma E divided by root of sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. Now if I substitute sigma 3 as 0, then rest of it, sigma 1 is 70, sigma 2 is 70, yield point is 100, so n is equal to 1.43. All this I have computed based on our regular 5 theories of failure equations, and all these equations are available in data handbooks. Mahadevan and Balvera Reddy or any other handbook can be also used. Lingaya or PSG data handbooks are also available, and Patil and so many other handbooks are there, and all these equations are available in the regular handbooks. Now the same problem, if I solve using MATLAB, now I have to input sigma 1, sigma 2, sigma 3. So here, first thing what I do, clear screen, and I clear all the data inputs so that I can input my data here. So sigma 1, sigma 2, sigma 3 I have to input. Then yield point stress 100, that also I should input, and Poisson's ratio, which I take 0.3, also be inputted. So first thing is I give initiation for all my values, sigma 1, sigma 2, sigma 3, sigma E, and Poisson's ratio mu. Now here this 3 stress, sigma 1, sigma 2, and sigma 3, I can represent it in the form of a vector, principal stress vector. It's a row matrix. It is a row matrix, and I sort it in the descending order so that sigma 1 comes first and sigma 3 comes last in that order. Now once I do this, I'll apply the first maximum principal stress theory, right? So maximum principal stress theory, according to this, factor of safety will be sigma 1 by sigma E by sigma 1. Sigma 1 is what? Maximum of the principal stress. So I am taking from the principal stress vector maximum principal stress, that is sigma 1. Sigma E yield stress is nothing but sigma E by sigma 1. Then maximum shear stress theory. This is maximum principal stress theory. This is maximum shear stress theory. So here again I can put this into the form of a vector. Sigma 1 minus sigma 2, sigma 2 minus sigma 3, sigma 3 minus sigma 1, and then put it in the descending order, and whichever is maximum, the first value will be maximum. So maximum of these three values I will take here. So sigma E divided by maximum of sigma 1 minus sigma 2, comma sigma 1, comma sigma 2, I get here. Then maximum principal strain theory. See here, sigma 1 divided by, sigma E divided by sigma 1 minus mu sigma 2 plus sigma 3. This is factor of safety according to maximum principal strain theory. And then total strain energy, sigma E divided by square root of sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 mu into sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. And then lastly, distortion strain energy theory, factor of safety according to distortion strain energy is sigma E, yield point stress, divided by square root of So once I enter the entire code, here it is asking me enter the maximum principal stress PS1, that is sigma 1, which we have 70 here. Then sigma 2 also I have 70. Sigma 3 I have 0. Then yield stress, we took it as 100 in the problem. And the Poisson's ratio is 0.2. Now when I do this, you can see here, according to distortion strain energy 1.42, according to total strain energy 1.207, according to maximum principal strain theory 2.04, according to maximum shear stress theory 1.4, and then according to maximum principal stress theory it is 1.4286. I think it is comparable there. Just see all the values there. 1.43, 1.43, 2.04, then 1.207 and 1.43. All exactly they obtain the same values there, even using the MATLAB code. Similar, same code can be also used by changing the values of sigma 1, sigma 2 and sigma 3. You can do it, the same code I'll share with you. You can check with the different values of sigma 1, sigma 2 and sigma 3. And consider a second example. Given a 3D state of stress, here sigma x, sigma y, sigma z, tau xy, tau yz, tau zx. These 6 components are given, and the yield stress is given as 10 MPa, and Poisson's ratio is 0.3. You have to determine the factor of safety. In that case, you can see this is sigma x is 1, sigma y is -2, sigma z is 4, tau xy is 2, tau xz is 1, tau yz is 1, tau zx is -3. So sigma x, tau xy is 2, tau xy is 2, tau xz is 1. Yeah, tau xz is 1. This is how all the 3 normal stresses and 3 shear stress components are given. In such case, how to determine the factor of safety? First, I will obtain the conventional solution. Right, this is based on invariance. Right, so Invariants are the values which do not change even if we change the frame of reference. That means coordinate systems. Usually we call them as tensors. If we are able to transform from one coordinate system to another coordinate system, such parameter we call them as tensors. Now, suppose xyz is my coordinate system, then if my invariants, you can see here, this is a cubic equation whose roots are sigma 1, sigma 2 and sigma 3. And I1, I2, I3 are called as first, second and third invariants. Now, if xyz is a coordinate system, I1, I2, I3 are its invariants. Suppose we transform from xyz to some other frame, frame of reference, like such as x dash, y dash, z dash. In that case, the values for sigma x, sigma y, all the stress components will change. But only this I1, I2, I3, even if it is I1 dash, that will be I1 only. I2 dash is also equal to I2, I3 dash is also equal to I3. So that means there is no change in these invariants. Rest and all will change. So such values are called as invariants. Now I know sigma x, sigma y, sigma z. I will find out I1, I2 and I3. So this is the equation that is given to find out I1, I2, I3. And when I'll substitute these values here, you can see here I1 I got, I2, I3, and this is the equation, the cubic equation. By using a simple calculator, I can get all these three values. By inputting the equation, I can get this solution. So 5.25, 1.95 and minus 4.2 arranged in order, right? And again, I'll apply all the 5 theories: maximum normal stress theory, sigma E by sigma 1, maximum shear stress theory, whichever is largest out of these three. So again that one, and then maximum strain theory, sigma E by sigma 1 minus mu into sigma 2 plus sigma 3. This is I get in here. Total strain energy sigma E by root of sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 mu sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. Substitute all these values, I get again n here. Distortion energy theory, sigma E by root of sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 sigma 2 sigma plus sigma 2 sigma 3 plus sigma 3 sigma 1 under root. So this again will give me the factor of safety. I have all the 5 factor of safety. Now in this case, I am given with sigma x, sigma y, sigma z, tau xy, tau yz, tau zx. That is a 3D state of stress was given, from which I get the values of sigma 1, sigma 2 and sigma 3. But when I apply the code, I can make it much more easier. For inputting all the 6 stress components, you can see here, sigma x, sigma y, sigma z, tau xy, tau yz, tau zx, and then yield stress, sigma e, and then Poisson's ratio 0.3, that also has to be input. These are the inputs that I have to give in the beginning. Now, the stress tensor, you can say in the matrix form, as all the 3 by 3 matrix I get. If I give a command called eigenvalues, then automatically it will give me the values of sigma 1, sigma 2 and sigma 3. All 3 values will be obtained. If I put it in a row vector, then I get it in this order. And sorting out in the descending order, I get sigma 1 first, sigma 2 and sigma 3 in that order. Then again, principal stress theory, sigma E by sigma 1, maximum value of all these 3 is sigma 1 here. And then maximum shear stress theory, out of sigma 1 minus sigma 2, sigma 2 minus sigma 3, sigma 3 minus sigma 1, whichever is maximum, by arranging it in the descending order, the first value I get the maximum value. So sigma E by maximum value of between sigma 1 minus sigma 2, sigma 2 minus sigma 3 and sigma 3 minus sigma 1. I get the factor of safety. Maximum principal strain, again sigma E by sigma 1 minus mu sigma 2 plus sigma 3. Total strain energy, sigma E by root of sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 mu sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 1 sigma 3. And lastly, distortion strain energy theory, sigma E by root of sigma 1 square plus sigma 2 square plus sigma 3 square minus brackets open sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 1 sigma 3. This is the code. I think I'll show it how we get the results using the code. Whatever code I have shown you just now, same thing I am copying and pasting in the workspace there. So I have to enter now all 6 values, right? And these 6 values are 1, minus 2, 4, 1, minus 2, 4, then 2, minus 3, 1, 2, minus 3, 1. Yield stress is given as 10 and Poisson's ratio is 0.3. So you can see here, take you back quickly. So the stress tensor, whatever I had shown you earlier, and the principal stresses we have PS1, PS2, and PS3, and then we have to arrange it in order. You see here, it is arranged in descending order. We get sigma 1, sigma 2, and sigma 3, and same values of factor of safety according to maximum principal stress theory, according to maximum shear stress theory, maximum principal strain theory, total strain energy theory, and distortion strain energy theory. Exactly the same values we get whatever we have calculated for by conventional method. And let me take a third numerical, that means different kinds of inputs we are giving. Here, diameter of the shaft and load on the shaft is given. And the loads that are given, one is axial load is given, bending load is not there, twisting moment is given. Given the yield point stresses 328.6 MPa, applying various theories of failure determine the factor of safety. And we know axial load is load by area, sigma x is equal to, I get sigma x. Then torsional shear stress is given at so tau xy I get, and then sigma y is 0. In this case, it is easy to find sigma 1 and sigma 2 because sigma 1 is sigma x plus sigma y by 2 plus root of sigma x minus sigma y by 2 whole square plus tau xy square. Sigma 2 is equal to sigma x plus sigma y by 2 minus root of sigma x minus sigma y by 2 whole square plus tau xy square. Here only thing is sigma y is 0. By doing that, I get the values of sigma 1 and sigma 2. Now, by sorting it out and applying that rule as done in the previous case, we get maximum normal stress theory sigma E by sigma 1. I get the factor of safety. Maximum shear stress theory, again I have only sigma 1 and sigma 2 because sigma 3 is not there. It's a biaxial state of stress here. And then according to maximum strain theory, sigma E by sigma 1 minus mu sigma 2. Again, total strain energy sigma E by root of sigma 1 square plus sigma 2 square minus 2 mu sigma 1 sigma 2. And distortion energy sigma E by root of sigma 1 square plus sigma 2 square minus sigma 1 sigma 2. I get all the factor of safety for various, according to various theories of failure. This is by conventional method. Again, I have the MATLAB code again, but what is the first thing that we have to do is we have to input the diameter of the shaft is given, then axial load is given, bending load is not there, it's a 0, but just put it in the code. So suppose if that value is given, even that we can calculate, then torsional moment and then yield stress, stress at elastic limit, and Poisson's ratio. You can see here the area pi by 4 d square. So stress sigma x is F by A. And bending stress sigma B, we have given the equation m by z, but in this problem it is not there, it is 0. If the axial stress is tensile, then it is total stress will be sum of these two. If it is compressive, then it is minus and plus. Okay. So here sigma y is already 0. Tau xy is the torsional shear stress T by Zp, that is T by Zp. And then stress tensor, now we have only biaxial state, sigma x, sigma y, tau xy. Now if I apply eigenvectors, then directly I get sigma 1 and sigma 2. You can see here the principal stress vector, that is rho vector, sigma 1 comma sigma 2. From here, once I get sigma 1 and sigma 2, maximum principal stress theory says factor of safety will be sigma e by sigma 1, maximum of sigma 1 and sigma 2. Maximum shear stress theory, again, whichever is maximum between sigma 1 minus sigma 2 and sigma 1, that will be taken. So sigma e by maximum of this value. Maximum strain theory, again sigma e by sigma 1 minus mu sigma 2. Total strain energy, sigma e by it is asking for diameter now. I can put the diameter. Diameter is 30. This is the axial load given in the question. So D is 30. Then axial load. Bending load we have not, we have taken it as 0, right? Then torsional load is so much. Then yield point stress 328.6 and Poisson's ratio is 0.3. Now with that I get the various factors of safety, and according to distortion strain energy theory, according to total strain energy theory, according to maximum strain theory, according to maximum shear stress theory, and according to maximum principal stress theory. All the 5 different theories of failure, so you can see here. So with that, we have successfully applied the MATLAB code for theories of failure given different conditions, loading conditions. In the first case, we had only 3 values, sigma 1, sigma 2, sigma 3, given the material property in the form of sigma E and Poisson's ratio. We could get the factor of safety according to various theories of failure. Then given the stress tensor, that means the 3D state of stress, and also the material properties in the form of sigma E and mu. Again, we could predict the factor of safety. And as a third case, when the diameter was given, diameter of the shaft and axial load and torsional loads were given. In that case, again, we determined the factor of safety, both conventional method and also the MATLAB code implementation. So this is one example as to how we can apply MATLAB. One particular example, that is theories of failure under static load. So this one example I think I have shared with you with enough amount of depth understanding of what the theories of failures are, and under what conditions these theories of failure need to be applied. With that, I have come to the end of my presentation.